It's time again for some more identity work. And this time we're going to get to the last two of the big three, sine and tangent, and their sum and difference identities, since we just derived for cosine. So what I'm going to start us all off with is the fact that we know that sine and cosine are co-functions of one another. And therefore, we can say that if we had the sine of some angle, and again, we'll call it a plus b for this one, then we know that that is equivalent to the cosine of 90 minus that angle. And because that we know that, then we can use the fact that even though we're trying to find the sine of this angle, we're calling a plus b, then we can say that cosine, and this would be our first angle, for lack of a better letter, and this would have been our second. Okay, but what I'm going to go ahead and do is I'm going to rewrite this as the cosine of, that would now allow me to couple the 90 minus a together and then have minus b. So there's my difference set up for cosine. So I'm going to have the cosine of this first angle, 90 minus a, and then minus my second angle, which we called b. And if you remember, we just derived this in the last video, that the cosine of an angle, which again we're calling 90 minus a, minus another angle is equivalent to cosine of the first times cosine of the second. And then remember, since it's cosine, which is the x value, we do the opposite sign, so it's going to be a plus there, and then sine of the first angle times sine of the second. Now, of course, just like we started out with when we said the sine of an angle, even though it's a sum, we knew that that was equivalent to cosine of 90 minus that angle. So if we have 90 minus that angle for sine, then we can obviously rewrite that as cosine of the angle. And then cosine of 90 minus a, like we just mentioned up here, would be sine of that angle. So rewriting those, we would have, and that would be our simplified form of, remember what we had on the left side of this equivalent statement or equal sign was the sine of a plus b. And so therefore, we now have our sum formula for sine. It's the sine of the first, cosine of the second, and then cosine of the first, sine of the second. So however you want to memorize it, just notice that you have the two different functions, sine and cosine, with the two different angles on either side. You just have to switch them for the second pairing. Okay? So pretty simple, just utilizing our previous derivation of cosine coupled with the fact that we know the cofunctions of these things as well. So doing a similar version of this using our, now what we have, the sine of a plus b, the sum formula, we can rewrite the sine of a minus b by getting just a little creative and putting plus a negative, which is the same as subtracting, because then that would allow us to look at this as the sine of a plus some other angle we're going to call negative b. So these are indeed equivalent. We're going to go ahead and do the sine of the first, cosine of the second angle. And then remember, because it's sine, which is our y over r, y's are y's, we'll keep the signs the same. Then we would do the switch. I like to keep the sine and the cosine, sine and the cosine, and just switch my angles. All right, but we have some negative angles that we don't particularly enjoy. We'd rather have positive. So what does that mean that we could do? Hopefully you recall, when we have negative angles, we can just focus on the fact that the positive angle would most likely be in quadrant 1, 2, 3, or 4, of course, but we're just going to think that it's in 1. So if we had theta here, then we could do negative theta here. And that would allow us to look at the all students take calculus. And that's what we said, that cosine would be the only one that stays positive. We call that an even function. Okay? So this one, we can just take the negative and write it as a positive, but the sine would be a negative for that same angle. So what we're going to do with this is just simply take it out in front of the negative. So that would leave us with, just cleaning that up, the negative would now become the same cosine of that angle. And then the negative for sine, we said we could bring out in front. And since we're adding a negative, that becomes a negative. So remember what we just found on the left side that is equivalent is the sine of A minus B, the difference of two angles for sine. It's the sine of the first, cosine in second, minus, remember sine stays the same in sine, sine of the second, cosine of the first angle. All right? So not too bad, pretty simple, a lot easier derivation than cosine, but we also need tangent. So before I give you that, here they are for sine, nice and simple, all concise in one neat form. Now notice that the book is going to give it to you as the angles always in order, AB, then AB, and again notice sine is the Y over the R. So remember when we were graphing, Y were Y's. We listen to them. We'll do the same thing for these identities. Okay? Now what I like to do though is, instead of rewriting the angles in the similar form and flip-flopping the sine and the cosine in the second part, I like to keep the trig functions the same. Sine of A, cosine of B, and then writing it as the sine of B, cosine of A, switching the angles instead. Okay? It's totally up to you. It will end up being the same because we are multiplying, and the commutative property will work as long as you keep your signs the same in sine and making sure that you switch something. Either the two angles staying the same and switching the sines and the cosines, or keeping the trig functions the same and flip-flopping their angles. Okay? Got to memorize these as well. Again, it's a lot, I know, but the good thing is I'm going to give you guys a nice, concise page of notes for this entire chapter 5 and all the identities, at least their generic form, and then you can use them as well as manipulate them to get what you may need or want. So let's get to tangent. Now that we have sine and cosine, we want to make sure that we can find something for tangent. But if you remember, we already knew that tangent was equal to sine over cosine of that specific angle. So of course, let's start off positively. Let's start with the sum, and then we'll get to the difference for tangent. So the first thing we're going to do is rewrite this as the sine of that angle, which happens to be an A plus B, over the cosine of that angle. Now the cool thing is we already know these, so we can take this an easy, quick step further and go ahead and rewrite the top as sine A cos B plus sine B cos A. And then doing something similar for the bottom. Remember, for cosine, we do cosine and then sine. Of course, of both angles. And remember, cosine is the x, so we will do the opposite. Now, of course, that's pretty ugly. We're going to try to simplify that. And don't forget the end goal, kind of like our verify problems, we want tangent. So if I want tangent, I remember that as sine over cosine, then I want to get rid of the cosines and put the sines over cosine. So I'm going to go ahead and, just like we've been doing many times over, multiply by a fancy 1. And that 1 is going to be 1 over the cosine of A cosine of B. So that will get rid of that and will make this a nice tangent. We'll deal with the repercussions on top. By distributing this to both the top and the bottom, each of those 4 pieces, I kept it color coordinated for you so you can see the red parts are still there, the green parts are what we distributed. So now we have all of these fractions within our big fraction. And of course, we want to try to simplify this. So that then would allow us to cancel out some things because remember, only time we can do that is when we're multiplying, and anything divided by itself becomes a 1, and also here, and a few other places. So then the things that are left that aren't multiplying or dividing by 1s are the sine A over cosine A, which that would then yield tangent of that angle A. And then here it's a sine B over cosine B. So now I have tangent of angle B, and that's my new numerator. In the denominator, all of this became a 1. We do have to put it, remember, we're mathematicians, not magicians. It doesn't just disappear, all right? And then minus this one, a little bit uglier, because we have the sine A over cosine A. That is the tangent of A, but then it's multiplied by the sine B over cosine B, which is the tangent of angle B. And that is as good as we can get, which remember was this, which is equivalent to that. So our answer for the tangent of A plus B is equivalent to the tangent of A plus tangent of B on top, because remember that was the sine, so the sine stays the same. And then on bottom, remember it was cosine, but it's 1 minus. Sines are going to be different. Tangent of A, tangent of B. So tangent is not as nice because it is a fraction in nature. And remember, we already, when evaluating trig functions, typically get fractions. So this is going to end up being pretty complex for tangent, where sines and cosines are pretty nice, because even though these 4 things are typically fractions, we can just multiply and add or subtract for sines and cosines. Okay, but for tangent, unfortunately, we're going to have fractions within fractions. But there is one good thing about tangent. Notice that these 2 are the same and these 2 are the same. Where with sines and cosines, there are 4 different values for each of these. So we would have to evaluate 4 trig functions for either of those, where here it's just 2. So that's the one nice thing about tangent. Otherwise, we much prefer sine and cosine. So now that we have the tangent of A plus B, let's go ahead and find the difference now that we have the sum. By doing very similarly like we did with sine and putting plus a negative angle and doing all of that the same type of way. But you guys know that if we just use this, the tangent, because if we threw a negative here and here, that would just make these change their signs. And therefore, I'm just going to give it to you without deriving it. So here it is. Now we would have tangent of A minus B. Now this sign would be the same, and this sign would be different because of the sine over cosine. All right? So pretty nice. There's the big 3. The cool thing is we will not find the other reciprocal functions, secant, cosecant, or cotangent. Instead, we'll just try to rewrite it in these because we got enough already on our plate. All right, so that is it as far as new material goes. Short and sweet here, not too much going on, just adding in both the sum and difference formulas for now sine and tangent. All right, so let's get to the examples. Hopefully you're ready. And again, feel free to pause it at any time and try to work it out ahead of time. Otherwise, I will go through and explain them for you. So here's example 1, and notice they're asking us to find the exact value, meaning that they want you to leave the pi's in the answers and not approximate. Okay? So you need to remind yourself that what they gave us was the sine of negative 15 degrees. We cannot change that. We have to evaluate what they gave us. Now again, you could just punch that in your calculator and get out some long decimal approximation, because we know that is not one of our reference angles in any quadrant, but it is something that we can work with as far as reference angles go. So I'm going to still have the sine, but I'm going to have to get a negative, obviously we're going to be subtracting. And whenever I told you guys there's a 5 involved, you're going to have to use 45. So you should hopefully thought of 30 minus 45. That, when subtracted, is equivalent to that. So I still have what they gave me, just in a new form. And now you either look up until you memorize what the difference for sine is, and it is sine of the first angle, cosine of the second, and then remember sine, we keep the sign the same because it's the y over r, and then we'll do the sine of the second times cosine of the first. And all we have left to do, just like the previous section or video, is evaluate. So let's evaluate those 4 things and see what we get. And again, hopefully you have these memorized by now. Sine of 30 is 1/2. Cosine of 45, root 2 over 2. Sine of 45, also root 2 over 2. And the cosine of 30, since we knew sine was 1/2, this would have to be the other 30, 60, 90 ratio, which would be root 3 over 2. Now remember, you're going to have to do the order of operations, which is multiply straight across and then subtract. So that would yield which then allows us, since we have a common denominator, to keep it and do what it says on top. And that says to take the square root of 2 and subtract the square root of 6. And since we can't, we will leave it like that. Okay, again, answers should look very familiar. We've talked about that before. You're going to see a lot of these because of our reference angles and getting a lot of the same results or outputs. Okay, so if you want to try part B, go ahead. I wanted to give you one that was both sine and tangent, and one that was both degrees and radians. So go ahead and pause it, give that a try. I'll come back and explain it to you. It may be a little bit different than what you did it, but remember, as long as you get the end result and can show me how, that's all that matters. All right, hopefully you're okay with radian measurements. Again, remember, we're trying to find the exact value. So how are you going to use pi? Remember, we said pi is equal to 180, as well as the 3.14-ish. But in this case, we're dealing with an angle measurement for this trig function. So I'm going to go ahead and rewrite that 13 pi over 12, because that's harder to work with in order to find sum and differences. And I'm just going to change it to degree measurement. So I'm going to rewrite this pi as 180 degrees, or you can go off to the side and multiply by that fancy one. Once again, told you guys it was an important concept of 180 degrees over pi, so that my pi's will cancel out. And then I can just virtually divide the 12 into the 180 and then multiply by 13. Okay, and that will give you 195 degrees. Okay, so once you have that, again, notice it has a 5 in it, and therefore I know I'm going to be using the 45. But also notice that we do not only have to play in quadrant 1 like we had in the previous. 195 is going to require some larger angles. So is there something that I can take with that 45 degrees and obviously add to get to that larger one, to get 195. Because remember, once again, we cannot change 195 degrees. We can just change the look of it. And obviously, 150 plus 45 would get me to 195. And as long as I know this, it is a reference angle, possibly in a different quadrant, then we're okay. And 150 is 180 less 30. And that's perfect because that means we have a reference angle, just playing in quadrant 2. And because I now know the tangent of A plus B, I'll write tangent of A plus tangent of B. And then on the bottom, it's 1 and then the opposite sign because that's the cosine, which is tangent A, tangent of B. Now all I got to do is evaluate those 4, and technically it's only 2. And once I have those 2 things, I'll then punch those in and then try to simplify this big, nasty, what we like to call complex fraction. So as I mentioned previously, the one nice thing about tangent is that it has 2 of the angles that are the same out of the 4. So we really only need to know the tangent of 45, which you should remember is your favorite one because it is 1. And then the tangent of 150, you got to be careful, all right? Tangent of 150 means that we're going to go 180 and then back that 30 degrees. But don't forget, we're in quadrant 2, which means it's going to be a negative value for tangent. Okay, so all you have to have memorized is your reference angle for tangent. That is 30. And 30 degrees is root 3 over 3 for tangent. All right, so not too bad looking because of the ones, but we do not like the fractions within fractions. And that requires us to go ahead and multiply one more time this big old thing by, I'm going to get rid of the denominator of 3. So I'm going to multiply both the top and the bottom by 3 for my fancy 1. Now don't forget, that means you got to do it to both parts. Since these are multiplied together, that's all one part, and that would give us an answer of, multiplying this out, the 3 times the 1 gives me the 3. Positive and a negative multiplied together gives us a negative, and then the 3's would cancel out there to just give us a root 3 on top. Then the 3 times the 1 would give us a 3, and then a negative times a negative would give us a positive, and then again there the 3's would cancel, and since it's 1 times that, we're left with the root 3 on bottom, which unfortunately is a problem. We don't like dividing by things we don't even know, so we're going to have to one more time multiply by a fancy 1. And this time that 1 is going to be what is called a conjugate, which is just the changing of the sign between the a and the b term, the 3 and the root 3. So multiplying that all out on both top and bottom, we would get 3 times 3 is 9. 3 times the negative root 3 is negative 3 root 3's. And then when I distribute the next thing, I get another negative 3 root 3's for a total of negative 6 root 3's. And then a negative times a negative is a positive, and root 3 times root 3 is root 9, or 3. So that's how I got the numerator. The denominator, I don't have to FOIL distribute out the whole set because they are conjugates. So I only have to do the first 2, which is 9, and the last 2, which is a negative 3. Now, cleaning this up just a touch, we would be able to get the like terms together. 9 and 3 is 12 minus 6 root 3. Be very careful. A lot of students will make the mistake of actually combining 12 minus 6 and putting 6 root 3's. But remember, this represents 12 ones, and this represents negative 6 root 3's. So therefore, we can't combine those because they're not like terms. But in the denominator, these are definitely like terms, so 9 minus 3 is 6. Now don't forget what this right here represents. It tells us to divide. And since it's under each of these 2 pieces that are trying to be subtracted together, even though we said we couldn't, we can, however, divide. by the 6 into each of those. And so that would leave us with or what a lot of people like to do is just cancel. Now, be careful and don't forget that you have to cancel into each if you're going to do that. So don't just cross out the 6's. You'd also have to divide it into the 12. And so that would leave us with a 2 minus 1 root 3. So a lot more algebra involved when dealing with tangent. You can see, where can I go wrong? This is where we started this problem and changed it to degrees because it was easier to work with. Then we used the identity, and that was it. From there on out, it was a lot of algebra with some trig evaluations, evaluating the tangent of 45 for the 1's, and then the 150 for the negative root 3 over 3. From all of that point on, it was all algebra and memorizing all of those different things that we've learned up to this point, multiplying by a conjugate pair, getting rid of our fractions. Notice how many times we multiplied by 1. Again, I told you, very important concept. Then combining our like terms to then divide or cancel to get our final answer, which looks a lot easier than what actually transpired to get it. So hang in there, be nice, neat, and organized, because yes, there are plenty of places to make a mistake on this, especially right there with the negative root 3 over 3. Okay? So the last one I'd like you guys to try before we move on to example 2 is right here. And notice it already looks familiar. So go ahead and pause it, give it a try if you'd like. Otherwise, here we go. This, hopefully you recognize, looks like the tangent of A minus the tangent of B over 1 plus tan A tan B. Remember, these identities are identical. The left is equal to the right, just as the right is equal to the left. So in this one, we're actually working in reverse, backwards, if you will. They have already given us that form that we are going to memorize. All we have to memorize is, what is that equivalent to? And in this case, remember, tangent is sine over cosine. So I know that my sine is going to stay the same. This was the opposite. So I know it's going to be 100 minus 70 for this tangent representation. So I know that that is equivalent to the tangent of 100 minus 70, which is 30. And therefore, I can rewrite this whole thing as that. And of course, we can actually simplify that and evaluate to get root 3 over 3, like we just reviewed in the previous part B. Okay, so not too bad for those, obviously, very simple when they're given to you in the exact and proper form, which of course they won't always. Okay, but if you notice that and you recognize it, then rewrite it in its alternative form, simplify it, and evaluate it. So again, this is for anyone that would like to try another on their own or even see me do another example. But again, you can see it's very similar. The one difference is I'm going to do the sum rather than the difference of two angles. Okay? So a lot of times they're going to give you 2 so that you can work this out. And remember, they're going to also have to tell you where it is in one way or another. All right? So I'm going to go off to the side here and I'm going to go ahead and draw it. If you'd like to go ahead and pause it and try this one on your own from start to finish, there is a part C. I do want to know the quadrant of it. By it, I mean A plus B again. So I always like to start by drawing it. You could also start by just rewriting the sign of A plus B, but I'm going to go ahead and start here because I already know what I'm going to have to do in order to find these two things. Okay, so I know that A, my angle, was between pi over 2 and pi. So we're in quadrant 2. Then I'm going to do angle B, which is between pi and 3 pi over 2 in quadrant 3. And I also know what things are going to be positive and what are going to be negative based on their direction. So I'll go ahead and fill all those in so that I don't accidentally leave one of those out and make a mistake somewhere. Okay. Next, I'll go ahead and take what they gave me and fill that in. And since it's sine, I know that this is a y and this is an r. So going to angle A, I will say that my y is 4, my r is 5. So you should already know that this is a Pythagorean triple and my x is a 3, 4, 5. Okay. Next, I'll go to angle B, and because it's cosine, I know that this is an x over r, and I already took care of the negative there. So the x would be a negative 5, which we already have the negative out in front, and the r would be 13. And again, hopefully you recognize that this is a Pythagorean triple, and you would be able to skip having to do the Pythagorean theorem, which shouldn't take you too long, but it is longer than just memorizing. So this would be a 5, what 13? 12. And now I know everything I would need to for angle A and angle B. So now I'll just start by rewriting the sine of A plus B and the tangent of A plus B. So that would yield. And now that I have these all set up, I know that I'm simply going to find each of their values. We call it evaluating, so that we can simplify this mess. So I'll start with the sine of A plus B. Some of these they've already given us, others we're going to have to find. So they already gave me that the sine of A is 4/5 and the cosine of B is negative 5/13. So all we would have to come up with on our own, which is why we did what we did over here, is the sine of B and the cosine of A. Just make sure you're playing in the proper places or quadrants. So the sine of B is the y over the r, which would be negative 12 over 13. Remember, don't lose your signs. And then the cosine of A would be the x over the r, which would be negative 3/5. And that's basically it. All you have to then do is multiply and add, which I already have set up, my common denominators. So that would give me negative 20 over 65. Two negatives multiplied together will be positive, and then that would be 36 over 65 for a total of 16 over 65. That would be my final answer for the sine of A plus B without ever even knowing what those two angles are. Pretty cool. Now I'll do almost the same thing, but for tangent. And for tangent, we know that we're going to have to evaluate only two things now rather than four. But they didn't give us any of those, so we have to find them. So the first one, what is the tangent of A? A is here, so it's the y over the x, or opposite over adjacent, and that would be negative, don't lose your sign, 4/3, which I know is the same as that tangent of A. Then the tangent of B, again playing in the proper quadrants, the proper triangle, the y over the x, which would be negative 12 over negative 5, or positive 12/5, because of the negative over the negative. Now the hard part that most students struggle with is merely the simplifying, the algebraic part, okay? Needing common denominators and all that, again, you can attack these however you see fit, but I'm going to go ahead and rewrite this. without the parentheses and changing those two negatives multiplied together to a positive, and then multiplying these so that I can then take this and multiply it by that fancy one of my common denominator of both the top and the bottom of 15. The LCD, we call it, the least common denominator. I'm going to multiply by 15 to everything on top and bottom. So doing that to all of these parts, don't forget to do it to the 1, would give me, that would cancel to be 3 into that would be 5. So I got that times that, which would give me my negative 20. Distributing here, that would cancel to be a 3. So I had 3 times 12, which gave me the 36. 15 times the 1 is 15. 15s here would cancel to just be 48. So simplifying that, I would end up with a 16 on top, and 15 plus 48 is 63 on bottom. So that I know does not have any common factors because 16 is 4 times 4, which are just a bunch of 2's, and 63 is not even. So I know that this is my final answer for the tangent of that a plus b. And so therefore, because we found that both sine was positive and tangent was positive, what would we be able to find for the quadrant of a plus b? Where is the only place that both sine and tangent are positive? Definitely not in quadrant 4. Here and here are individually, so that would mean it would have to be in quadrant 1. Okay, so hopefully that extra one helped anybody that maybe needed to see it again. Those are definitely the most difficult in this section, but like I said, a big puzzle. Hopefully you enjoy puzzles because that's what a lot of math is just finding the right pieces and using them in the right place. Okay, keep working hard, you guys. I know this is a little bit trickier than some of the stuff we've done before in Trig because it's more algebraic in nature, but if you practice it enough, it will get easier. Right? Hang in there. I'm here for you. Let's keep working hard. Until the next time, Alan out.